Welcome to this video in which we discuss pairs of random variables. So far, we have talked about single random variables. However, often we need to combine multiple random variables in order to describe a random process. When a stochastic process is explained by multiple random variables, these are said to be joint random variables. The probability model of joint random variables needs to contain both the properties of the individual random variables as well as the relationship between them. In a previous screencast, we discussed the example of a random process described by multiple random variables. This was the process of rolling two dice and looking at the sum on the upward faces. We called d1 and d2 the random variables represented by the numbers on the first and second die, and y the sum of d1 and d2. However, in that case, we were only interested in random variable y, so a single random variable was sufficient. But if we want to fully characterize the stochastic process of rolling two dice, we need to build the joint probability model of d1 and d2. Similar to the case of single random variables, also for pairs of random variables, we can use the joint cumulative distribution function. The formula, given in the slide, is very similar to the single variable case. Given two random variables x and y, the joint CDF is given by the probability of x being smaller or equal to any x in the range and y being smaller or equal to any y in the range. Also, the joint CDF has properties that derive directly from the probability axioms. These are discussed in more detail in the read. We can also define a joint probability mass function for discrete random variables and a joint probability density function for continuous random variables. These are again very similar to the single variable case. The joint PMF is the probability of x equal to any x in the range and y equals any y in the range, while the joint PDF is the second order partial derivative of the joint CDF with respect to x and y. Let us now build the joint probability model for d1 and d2. We can define this as a probability mass function. For this very simple case, this is given by 1 over 36 for any d1 and d2 in the range. The range in this case is given by d1 being any integer between 1 and 6 and d2 the same being any integer between 1 and 6. When we plot the joint PMF as we see on the right, we can observe that if, for example, we look at the outcome d1 equals 4 and d2 equals 3, we obtain a probability of 1 over 36. Note that this is a legitimate PMF because if we sum all the values over the range, we obtain a 1. When we deal with multiple outcomes, an important concept is the conditional probability. Basically, with conditional probabilities, we can model how our belief changes when we have a priori knowledge on the outcome of an event, which has an influence on another event. Let us first look at the case when we have an outcome x and y that can be found in an event set B, with the event set B being a subset of the event space. In this case, the conditional probability of x and y given B is simply found by normalizing the joint PMF by the probability of B for any x and y in the event set B, while the PMF is 0 elsewhere. Now we can apply this to the example of rolling two dice. Suppose we define the event set B as d1 even and d2 even. If we know that the outcome can only be found in this event set B, we can calculate the joint PMF of x and y given B. As shown in the plot and in the formula, this is simply obtained by setting to 0 any d1 and d2 outside the event set and normalizing by the probability of B the joint PMF for any d1 and d2 in B. Since there are now 9 out of 36 possible outcomes for which d1 and d2 are both even, the probability of B is easily obtained as 1 over 4. Also in this case, summing all the values in orange, we obtain 1. Another case of conditional probability is when we observe one of the variables in the joint probability model and we want to describe how our belief changes because of this observation. Then we can model this joint conditional PMF as the probability, for example, of x given y, which is obtained by normalizing the joint PMF by the PMF of y. And very similarly, we can define the conditional PDF in case we are dealing with continuous random variables. To obtain the PDF of y or the PMF of y, we can apply an important operation which is known as marginalization. When we have available the joint probability model and we want to obtain the PDF or PMF of a random variable of interest, we can marginalize overall other random variables. This simply means, for discrete random variables, summing overall values that the other random variable can take, so in this case summing overall y's in the range, while for continuous random variables the summation becomes an integral. Let us now see how this works in practice. In this example, however, we are no longer interested in d1 and d2, but in d1 and y, which is the sum of d1 and d2. The joint PMF for this case is similar. It is again equal to 1 over 36 for each d1 and y in the range, but this time the range has changed. d1 is still defined for all integers between 1 and 6, while y is defined for all integers between 1 plus d1 and 6 plus d1. Suppose that now we observe d1 and we want to know the probability of y given d1. The conditional PMF is obtained by normalizing the joint PMF by the PMF of d1. And to obtain the PMF of d1, we can use marginalization. Looking at the formula for the discrete case, we need to sum the joint PMF for all the y's in the range. This means summing over this direction, and when we do so, we obtain the PMF of d1 as given in the right plot. It should not be surprising that this is given by 1 over 6 for d1 between 1 and 6. Similarly, if we want to obtain the PMF of y, we need to sum overall d1's in the range. And this means summing in this direction, from which we obtain the PMF of y as given in the right plot. Again, not surprisingly, this is exactly what we obtained in a previous video when we were interested only in the random variable y. And now that we have the PMF of d1, we have all the ingredients to calculate the conditional PMF of y given d1. Suppose that we observe d1 equals 4. Then to obtain the conditional PMF, we need to set to 0 any d1 different than 4 and normalize the values of the joint PMF for which d1 equals 4 by the probability of d1 equals 4, which is 1 over 6. By doing so, we obtain the conditional PMF given in the right plot. This is given by 1 over 6 for any value in the range, but now the range has changed. Now it is between 5 and 10. In fact, if we obtain a 4 in the first row, then the sum can only be between 5 and 10. In this very simple case, it is also easy to find a more general formula which is valid for any d1. This is given by 1 over 6 for any y in the range, given by the integers between 1 plus d1 and 6 plus d1. When we look, for example, at d1 equals 2, we see how the formula works, because in this case the probability mass function of y given d1 is again equal to 1 over 6 for any y in the range, but now the range has changed and goes from 3 to 8. This concludes the screencast on pairs of random variables, where we discussed joint probability models, and we also touched upon conditional probability and the important operation known as marginalization. Thank you for listening.